introduction. So now today I'll be speaking a few words in line with our the set title, that is computational methods in chemistry, a recently developing a branch domain of chemistry that is that's basically a part of what you say like computational chemistry. So probably I will share the screen and then I'll just continue with my presentation. That's better. So I'll just share now. Once again. I believe my presentation is visible.
Sir, it's visible, sir. It is visible.
Fine. So, as it was introduced, today's discussion is on computational methods in chemistry. And what exactly is this computational chemistry? We just need to think at first. So, it was informed like the major stakeholders for this particular session will be the students who have just passed out +1 or +2. So I have tuned my lecture in such a way that it will benefit for them. This subject is a bit mathematical and that way, even though it's denoted with chemistry. So I have just tuned that lecture in such a way like it will be beneficial for a student who is just stepping into the domain of chemistry, or who may in the near future itself, you may just step into a domain of chemistry. So I'll just go to the next slide. So this title itself probably could be a bit new to many of you. Like what is this? Because we are familiar with the basic domains like inorganic, organic, analytical, those kinds of things. So what exactly is this computational chemistry? So in order for the benefit of the students who have just passed out this +1, +2, that's the major stakeholders for today's meeting, to the best of my knowledge. So for the benefit of them, I have arranged a lecture with this particular flow. I'll be starting with the basic branches which people are aware about, which students are aware about. Then I'll just mention like where this title computational chemistry gets fit in. Then I will tell you what are the basic formulations that we make use for computational chemistry, a bit into mathematics, quantum mechanics, and those kinds of things. And then I will tell you a few major applications in connection with this computational chemistry. That's the plan for today's lecture. So before going to the details of this, I'll just tell you an experience that all of us might have had in nearly last 2 years. All of us were damned with the strike by our COVID-19, isn't it? In 2019 December, it was first reported, and from there it was actually a run of that particular pandemic, and almost all of us have gone through several miserable situations. But please remember one thing, that within a span of this 1.5 to 2 years, most of us have got vaccinated. And some sort of drug molecules have already been developed for this also. It's not complete, but still the development is going on. But still, a vaccination was done. Means a vaccine was developed in line with this particular COVID vaccine. Almost all of us are vaccinated at least to the extent of 2 doses, the aged ones. Have you ever thought about what all the branches of science that sciences that could have been contributed to that? You have obviously techniques in biotechnology and fundamental chemistry, medicinal chemistry, all these things have contributed to that. Obviously, all these things have contributed. But we should understand that one among the major stakeholders with respect to that contribution is this particular branch, which is computational chemistry. With the advent of techniques in line with computational chemistry, without the advent of techniques in computational chemistry, this kind of fast development of drug molecules or vaccines and those kinds of things would have not been possible at all. That itself helps us to realize the relevance of this particular subject. So now into the talk for today. So as all of you are aware, there are various branches of chemistry, which you're all familiar with. I need not go through the minute details of each and every part, because in +1, +2, up to +1, +2, by the time you complete your +1 and +2 courses, most of you will be aware about the titles like inorganic chemistry, organic chemistry, physical chemistry, and probably to some extent you will be knowing about something like analytical chemistry. 4 major pillars with which the entire domain of chemistry is actually carried on. And inorganic chemistry, organic chemistry, you are very much familiar, right? The chemistry of carbon and also carbon-based compounds, even though this definition has gone obsolete right now, but just to give a basic idea about what it is, I'm just starting with that. So carbon and carbon-based compounds, based on that, you have the very big domain of organic chemistry. Then the conventional SPD block, F block, those kinds of things, metals, non-metals, those kinds of things, elements and their compounds other than that of carbon, they form the inorganic chemistry side. And the titles like thermodynamics, chemical kinetics, okay, electrochemistry, to some extent adsorption, and these kinds of things basically comes under the title physical chemistry. And the way in which chemical analysis are being done in real times, that's being generally titled under analytical chemistry. So these are 3 or 4 major domains of chemistry which all of us are familiar till now. Then where we can place this computational chemistry, where it comes, what exactly is this computational chemistry? Okay, so let us try to go to another way of classifying the subject domain of chemistry. See, the subject domain of chemistry can be classified into 2 major categories. You have pure theoretical chemistry and you have pure experimental chemistry. The previous slide says classification of this particular subject based on the nature of the content, what you are going to learn under this particular branch, whether it is an organic chemistry side, inorganic chemistry side. So the nature of the content decides which branch it belongs to as per this classification. Now in the next one, where we have given 2 another classes of the normal chemistry, where you write it as pure theoretical and pure experimental chemistry. In pure theoretical chemistry, you are going to make use of mathematical principles, pen and paper methods, and you will be analyzing the chemistry of systems using pure theory, rigorous theory, that basically mathematics itself. Because you know, underlying to every aspect of behavior of systems in nature, there is mathematics. So utilizing the concepts of mathematics, you can learn about the system. The very idea in science, in any branch of science, is to understand about the systems in nature, systems and processes in nature. To understand about those, we have these branches of sciences. So if using mathematical principles from the fundamental, if you try to analyze the existence of systems in nature, you will be working with pure theoretical chemistry, majorly by pen and paper calculations and all. And on the other extreme, in chemistry, you have another category like pure experimental, where the persons will be majorly focusing on the experimental aspects of chemistry. That means the wet lab. You'll be in the lab, you'll be working with different reagents, maybe conducting reactions and those kinds of things you'll be performing. And that will be pure wet lab based work. That also will give you an insight to the systems in nature, systems and processes that exist in nature. So these are 2 distinct but different, distinct ways of approaches to understand the chemistry associated with systems. So you have a pure theoretical chemistry branch and you have a pure experimental chemistry branch. Now your computational chemistry, actually what happens is there exists a huge gap between the results that you obtain generally from pure theory and pure experimentation. And as a computational chemist, the computational chemistry domain, we will be knowing like this computational chemistry domain basically bridges the gap between these 2 pure domains, like pure theoretical chemistry and pure experimental chemistry. The computational chemistry will be basically bridging the gap between, in general, it will be bridging the gap between pure theoretical chemistry and pure experimental chemistry. Even now, I have not told what exactly is there in this computational chemistry. Okay, so I'll just be moving to that. So you should understand computational chemistry as more as a method of approach to solve problems of chemical interest, as it is written here, rather than a pure branch such as organic chemistry or inorganic chemistry or physical chemistry. Because based on the method, see, theoretical chemistry is basically a method of approach to solve problems of chemical interest. Experimental chemistry is actually a method of approach to solve problems of chemical interest. Similarly, computational chemistry is also a method of approach to solve problems of chemical interest, rather than a core branch with content like as in organic, inorganic, or physical. Please understand the difference with respect to the content that happens in computational chemistry when you compare it with that of organic, inorganic, etc. The conventional branches of chemistry. So now going to the next, one more aspect, that is the importance of this computational chemistry. One more point I can say. Nowadays, the trend in any chemistry, any process connected with chemistry, probably in an industry, any process that is connected with an industry, the major interest will be to transform that particular process into as a green method. That means a green process. What is meant by this green process? If a chemical process is, for example, let me tell you, I'm just performing a synthesis, an organic synthesis of an organic molecule, and it includes, for example, let us assume about 20 steps, 20 different steps, and it will be utilizing so much of solvents and those kinds of things in each step. Like that, you have 20 different steps for a synthesis, just as you. Now, if I am able to design, with my knowledge of chemistry, if I am able to design a method which reduces these 20 different steps for the synthesis to probably 16 different steps, and with the 16 step itself, you are getting the final product, I am doing green chemistry. Suppose I am using maybe 1 liter of one particular organic solvent, probably xylene or butyl cellulose, these kinds of organic solvents. Suppose I am using about 1 liter of one particular solvent in one particular sequence of synthesis. I design the synthesis in such a way that I just need to make use of maybe 100 ml of such an organic solvent, that the process has been changed to that. Then also I am doing green chemistry. Now you might have understood like what is meant by this green chemistry. This is basically a green approach in chemistry. So the thing is like you tune the existing chemistry in such a way that it will reduce the hazardous effects of chemistry with respect to the environment. The hazardous effects that the chemistry contributes to the environment need to be minimized in a more safer way, in a more eco-friendly way. Okay, we need to perform the chemistry, the existing chemistry, and that kind of an approach in the existing chemistry is actually called as a green approach. And let me tell you, one of the major ways in which processes are transformed into the green line is by incorporating computational chemistry techniques into the processes. Because with the, for example, using a computational chemistry, using softwares and computer tools, nowadays we can actually design what will be the scheme of a particular synthetic process. So you can design in such a way like you can avoid probably unwanted reactions which may not give. For example, I may be doing about 100 different reactions and one may be hitting to the final product. The trial and error used to be numerous in earlier days. Now, using the computational techniques, what we generally do is using computers and softwares connected with chemistry, you model the molecules, model the reactions, and first itself predict whether that will work or not. If there is an ample chance for it to work out, then only you just need to go for that particular work in the wet lab. That means if it is not suitable there, then and there itself you can stop working with that. That means you can avoid the wastage. That means it's a green approach. That's what the case. You are avoiding unwanted reactions in a lab. Okay, so those kinds of in that context, and what I'm trying to tell you is in these kinds of contexts of these green approaches, this applied theoretical and computational chemistry is going to play an important role. It has started to play an important role. I don't say going to, it has started to play an important role, especially in medicinal chemistry and related things. Not only in medicinal, in synthesis and design of materials. So precisely what I do is every chemical process in general can have a design phase where we'll be utilizing the computational chemistry techniques. So that makes the entire process a bit more green, because unwanted things can be eliminated at that point itself. Steps and processes can be eliminated at that point itself with the knowledge that you gain out of computations on these chemical processes. So in this way also this particular subject is relevant. Now coming to the next, what you generally study in computational chemistry. I'll just tell you briefly about certain aspects connected with mathematics, quantum mechanics, etc. from this point onwards. So that's the way in which I'll just be progressing further. So basically, what exactly is in chemistry, what exactly we do, we try to analyze properties of systems. So as a chemist, here I mean systems means atoms, molecules, etc. in general. So we'll be analyzing properties of system. For example, we will say water molecule has got this much of dipole moment. The net dipole moment is this much. So what is that property? Dipole moment is a property of that particular molecule, isn't it? And that actually talks about the solvent behavior of that particular water system. So the property of a system is explained in terms of these kinds of the real characteristic of a system is explained in terms of these kinds of fundamental properties. So eventually in all this, our work connected with chemistry, we will be analyzing the nature of the system. We will be studying the behavior of the system. Effectively, we will be analyzing the properties of those systems. And it need to be assumed correctly that almost all properties connected with a system originate by virtue of the electronic structure and also a few other structural aspects connected with that. For example, dipole moment of a system do exist in water. The net dipole moment of the system of water molecule is not equal to 0. Why it is so? Because water is not a linear molecule. It's a bent molecule, as you are aware. So you have the oxygen and hydrogen with slightly different electronegativities. So a vectorial combination of the individual dipole moments, if you get, you will get a negative, you will get a resultant dipole moment in one particular dimension, in direction within that molecule. So from the value of the dipole moment, you are trying to predict the structural aspect of that particular system, isn't it? Now you know from where this dipole moment takes its origin. It is because of the separation, the straight line separation that happens between 2 point charges, isn't it? The product of the charge and the straight line distance of separation between the charge. This particular product is your dipole moment in a vector line. That's a way. So this is what I'm trying to tell is, and from where this particular charges and other things originate, from the electronic structure of that system. So it is to be rightly assumed that I have just talked only about dipole moment. You can go for any other optical property or electrical property or magnetic property or mechanical property. Wherever you go, the fundamental reason for a particular type of property exhibited by a system solely lies on the electronic structure of that system, as well as some other structural aspects, like the bond is actually the molecule is actually a bent molecule. There is a bond angle theta value that exists. If the theta value that exists in a triatomic molecule is 180, the molecule is linear. For example, carbon dioxide molecule. All of you are aware that carbon dioxide molecule is a linear molecule, isn't it? So by virtue of that, it has got certain aspects connected with it has got certain properties that certain properties are exhibited by that molecule in terms of electrical or in line with electrical or magnetic or optical types of behaviors. Okay, so basic properties of atoms and molecules, especially molecules, because as a chemist now we will be focusing more on molecules as of now. That is very much centered on the electronic structure, you can say so. And as a result of this electronic structure, even some other structural parameters like the geometry of the molecule and those kinds of things also do take part in defining properties of those systems. So we just need to think reversely. Properties, we need to study the properties in chemistry, and properties are dependent upon the electronic structure. So now we can think in the reverse line by analyzing the electronic structure, and you can predict about the properties. And you can learn about the system. That is done in computational chemistry majorly. I hope you understood the way in which we step onto the domain of computational chemistry. Majorly, the electronic structure of systems are studied using several techniques, and based on the information that you gain in line with the electronic structure of systems, you try to predict properties of systems, and with that you understand about the system. That's the purpose of this science. So by analyzing electronic and other aspects on structure of systems, the properties of systems can be studied. Now the next question comes. So we need to analyze the electronic structure. Let us say we need to analyze the electronic structure as the fundamental aspect. How to analyze electronic structure of systems, molecular systems in general? Probably molecular systems we can consider as of now. How to analyze? There comes the help from computational chemistry, which basically utilizes the very hardcore mathematics and also the applied mathematics regimes like quantum mechanics, molecular mechanics, molecular simulations, etc. These molecular simulations include several things like molecular dynamics simulation, Monte Carlo simulation, MC simulation, then CPMD simulation, and many other types of simulations. In general, I say simulations. So utilizing the techniques in computational chemistry, we will be in general analyzing the electronic structure and also other structural features connected with molecular systems, and based on that information, we will be predicting properties of those molecular systems, and we will be knowing about those molecules. That's the ultimate purpose of this learning. So computational chemistry is connected with it is connected with respect to gaining knowledge about the systems in nature. So I hope up to this it's clear. I'll just go to the next point. So in computational chemistry, as I've told you, we'll be dealing with properties of systems, and they originate majorly from electronic structure. We assume so. We rightly assume so. So what we will be making use in this particular context, we will not be, for example, if we were in a wet lab, if we were in a normal wet laboratory, for example, if I just need to study the property of methane, as you are aware, methane consists of an sp3 hybrid carbon. So the CH4 structure will be with the bond angle HCH angles 109 degree 28 minutes. That is the tetrahedral structure. This much we know already. But you don't, in a laboratory, in a normal wet laboratory, you can have a methane molecule in your hand. Probably you can have, in a real sense, you can have a molecule and then subject that molecule for very many number of experimental techniques and try to extract properties of those systems. That's what we do in pure experimentation. Now in computational chemistry, how you analyze probably the property of, let me say, methane, that molecule itself. So there we will be making use of computational models. You don't have a real methane molecule with you, but you have a real model of methane molecule that you have constructed using mathematics within your computer. So using methods of mathematics, there are and integrating the methods of mathematics with the structural aspects in chemistry, you can make models. You call them as computational models. So on the computer screen, you will see the methane molecule. Don't mistake it only for a picture. It's never a picture. I can just show you one particular representation here. I believe you can see all these things. For example, I'll just take up 1 second. 1 second. I'll just take the picture and we'll just show you. Yeah, just coming to that. See, here you can see that this is actually a small, this is actually a tool which is available worldwide in a free form. You can take it and then you can work out. Here we are just going to take carbon, bond order single. If I just click here, what I'm going to get here is a methane molecule model. Don't mistake it only for a picture. It is never a picture alone. It has got from this particular, this is basically a computational model of that molecule. For example, if I just take oxygen and do it, this is just a computational model that you can take up as for water molecule. If I just go for nitrogen and do it, this is basically your NH3 molecule, isn't it? So this is the way in which you generally take up the generally construct the computational models. I am just telling you one particular method. So you never mistake it only for a picture, because there is possibility that you are just plotting a tetrahedral structure and keeping it as some JPG image type of thing. No, it's not so. It's a model from which, using mathematical methods in the computational science language, you can extract almost all properties of methane itself. Whatever you can get from the experimental methods in the experimental lab, the same thing you can extract from this particular system also, this particular picture also. It's not picture, this particular model also, to be correct. So the computational model, that's what I have written. The computational model should almost be something like a real natural system itself. So atoms and molecules have to be realistically modeled in computer. That is done in computational chemistry. It's a part of work that is involved in computational chemistry. And in connection with that, whatever natural behavior of molecular systems do exist in nature, all those criteria, natural criteria, should be properly matched with the computational model that you make. Something close to stability, symmetry, quantization, homogeneity, these kinds of terms. I'm not going to the details of these terms right now, because these are all some of the natural. The thing is, like, some of the natural aspects that is associated with it should exactly mimic a methane molecule in reality, whatever model that you have made. A water molecule model, if you make, computational model, if you make, it should exactly mimic a water molecule in reality, water molecule in nature. It should exactly mimic. So all the properties of water molecule that exist for a real water molecule, we should be able to extract it mathematically from the model that you develop in a computer. That's what is generally done in computational chemistry. I've taken very simple molecules, but even huge molecules up to proteins, then solid lattices, these kinds of things are now being worked out. People are working on these kinds of things. Okay, so this natural criteria means it should fit. Natural criteria should be satisfied. That means that your model also should have the criteria, should fit to the criteria of stability, symmetry, quantization, homogeneity, these kinds of things. Basically, this is a general term that I have used. I'm not going to the minor details of these terms right now. So now let me go to the basic formulations. Now you have just understood what are the various branches where you can fit this computational chemistry. So it is, you cannot say that it is pure theoretical like pen and paper. You cannot say that it is purely lab like the wet lab work, but it is in between. It connects actually the theoretical to wet lab to some extent, to a considerable extent. That's what at the first one of the, in one particular what do you say, in one particular slide previous to this, we told like it bridges the gap between theoretical and experimental chemistry. That's how it becomes. Now let us try to understand in a very brief way. I'm not going to the details. From this portion onwards, the real mathematics starts. So from this portion, I'm not going to the rigorous mathematical part of that, but instead, I'll just tell you briefly like in what way these computational chemistry techniques have been formulated. So there are various methods with which computational chemistry works are being carried out. And let me tell you, one of the major branch of science which we make use in order to work in computational chemistry regime is mechanics. You have classical mechanics, you have quantum mechanics, and you have statistical mechanics. These three major domains of mechanics have been extensively utilized in computational chemistry formulations, the working formulations of computational chemistry. Okay, so why we are going behind mechanics? There is an interesting theory that you can understand in line with that. See, what is this mechanics? As you are aware, mechanics will be the scientific study of motion. As mechanics is scientific study of motion. That means why you are going behind motion associated with systems to study about the chemistry of that? Because motion is something that is a permanent aspect connected with any type of system that exists in the universe. There is no state of rest. Those who have studied at least a bit of quantum chemistry, quantum mechanics type of thing, they'll be knowing like there is no state of rest. In fact, if you go to the domains of lower and lower dimensions, atoms, molecules, and like that,
being recorded.
Okay, something is being told. Can I continue?
Yes, sir. Continue.
Yeah. Okay, fine. There was some other message. That's why I thought. Okay, fine. So this mechanics. So why we generally go behind this mechanics? We were talking about that. So we will generally be focusing on systems like molecules, and in the domain of molecules and all, there is perfectly no state of rest. So that
Sir,
means all
excuse me,
systems
sir.
have got at least one kind of mechanics aspects connected with that.
Sir, Deepak, sir, is it possible
Yes.
that you could share the slide again?
This one?
Slide. The slide is
I
not
think
visible.
that camera has.
Yeah. Fine.
Is this okay?
Yes, sir. Okay, sir. Okay, sir.
Shall I go for share screen again?
Sir, if you have anything to share, yeah, possibly.
No, that slide itself, correct?
Yeah. Yeah.
One second. I'll just go there. Can you see this slide now?
Yes, sir. Yes, sir.
Yeah, fine. So the really static part with respect to existence, that the aspect which is not at all changing with respect to the existence of systems in nature is only its motion, the motion associated with system. So that is why by studying the mechanistic aspects associated with existence of molecular systems, you will be able to understand about the system. That is why we are focusing on the mechanics part in order to study about the system. And this mechanics itself, as you are aware, there are various branches of mechanics, as you might have studied in physics. Like you have classical mechanics formulation, in which you assume that the energy change as well connected with a moving entity is actually continuous. The energy change is continuous. It is connected with our Newton's laws of motion. You have Newtonian formulation, Hamiltonian formulation, Lagrangian formulation, these kinds of classical formulations that we generally address under the classical mechanics regime. So there we assume that the energy change connected with a moving entity is not in discrete, but it is a continuous aspect. It could be true if you are analyzing a macro system and its movement. But when you move from a macro system to systems like atoms, molecules, electrons, protons, nucleus, those kinds of things, then you just need to change the focus from the continual change of energy associated with motion from that continual change to discrete changes. There comes the involvement of what you call as quantum mechanics. So when you move from the domains of macro systems to the domains of micro or submicro systems, in the quantum regime like atoms, molecules, etc., then quantum mechanics starts to play. So you have classical mechanics formulations, you have quantum mechanical formulations. Now for individual molecules, when you work out, you can use pure quantum mechanics itself. But when you are working with a huge collection of huge number of molecules in a collection system, for example, suppose I am trying to model 1 mole of an ideal gas, I am going to model its temperature. So I need to work about Avogadro number of molecules in that case, because each and every quantum mechanical aspect each and every molecule will be analyzed in the line with quantum mechanics. But what you experience is from bulk from the 1 mole of that system. So in that context, you will have to statistically average the contribution from each and every entity, and then you can possibly proceed towards the thermodynamic based computations. In that context, you will be utilizing the branch of statistical mechanics, or even in this context, statistical thermodynamics. So mechanics is why we are behind mechanics. We should understand it's just because motion is the only non-changing aspect associated with existence of systems, especially when you go to the world of molecules, atoms, etc. So by analyzing the motion scientifically, you can learn about the system. This is the basic philosophy of going behind this mechanics to develop formulations of computational chemistry. And when classical mechanics is applied to study molecular motion connected with molecules like rotations, vibrations, etc., you address that particular branch of computations as molecular mechanics based computations. Classical mechanics in general apply to study of molecular motion. And you have quantum mechanical computations too beyond this. So quantum mechanical computation means you will be solving Schrodinger equation and further you will be proceeding further in that context. Then statistical mechanics means you will be dealing with modeling of properties connected with bulk systems, utilizing what has been originated by quantum mechanical calculations for individual molecular systems. This is how the various domains, basic science domains, which contribute to the development of formulations in computational chemistry exist. This is how it exists. Okay. So now, just to make you familiar with the one particular mode of computation, one particular formulation, I will just give you a glimpse of one particular type of formulation, that is quantum mechanical computations. What exactly is done, very basically, if you think what exactly is done in quantum mechanical computations. So the quantum mechanical formulation basically involves solving the time independent Schrodinger equation in 3 dimensions to solve the electronic structure of the system concerned. For example, I just want to find out the total energy probably of water molecule. What I need to do, develop a wave function which represents the overall electronic structure of that water molecule and solve it in the Schrodinger equation. That is the very fundamental form of Schrodinger equation, time independent. As of now, I will be working only on time independent Schrodinger equation. So the very fundamental form of this time independent Schrodinger equation, I believe you might have studied this in +1 or +2, most of the students. So it basically goes with H cap psi is equal to E psi, where H cap is the Hamiltonian operator, that is the total energy operator, which includes the kinetic energy and potential energy terms. I believe I need not go to the minute details of these things because that will be more rigorous. And later, if any of you take up chemistry for further studies, so surely you will be going through much details of all these things. In our curriculum also, detailed courses on all these things are there. So this H cap is basically the Hamiltonian operator. Psi is called as a well-behaved wave function. It's a single valued, it's a finite, it's a continuous, it's a normalized wave function, which represent the overall electronic structure of that. So when the total energy operator acts on the well-behaved wave function representing the electronic structure of water molecule, I will get the total energy connected with electronic energy connected with water molecule. And based on that value of energy, I can actually predict almost all properties connected with that system, because you know, almost all properties of systems are manifestations of the total energy content of that system, or whatever that we do. The total energy content, if you are able to extract, then based on that, you can predict most of the properties connected with that system. That's what is done here. So solving Schrodinger equation, this is a mathematical procedure, you know, this is basically a second order partial differential equation, because H cap is basically something which includes your if I say the detailing of that, it includes like minus h cross square by 2m into del square plus v. That is the very basic expansion for your H cap, where del square is basically the Laplacian operator, which is fundamentally a second order partial differential operator. That is dou square by dou x square plus dou square by dou y square plus dou square by dou z square. That way it exists. So effectively, this particular equation, which you call as an eigenvalue equation, is basically a second order partial differential equation to solve. So the mathematics involved is that much. So utilizing the mathematical principles, you solve it in order to get the energy of that system. And based on that energy, you can predict the property of that system. Suppose I'm working with the pi electronic energy of benzene. I take the pi electronic structure of benzene and develop a well-behaved wave function for that particular electronic structure in benzene, and take the Hamiltonian operator corresponding to that benzene and operate this Hamiltonian operator on the wave function, and the solution that I get, the eigenvalue that I get as a result of this particular operation will be operation on that function will be the eigenvalue, that is the energy of that system, pi electronic energy of that system. So the essential work that is involved in quantum mechanical computation, one major type, is basically just solving in a single statement, I can say it's just solving the three-dimensional time-independent Schrodinger equation for that given system. I'm not going to the minute details of mathematics now. Now I have 15 minutes more, it seems. So probably I will go through some of the quantum mechanical formulations, some more ideas on quantum mechanical formulations. And obviously, you know, we need to take up certain approximations when you proceed with quantum mechanical calculations. Okay. So what is meant by this approximation? For example, one thing I can just tell now, Born-Oppenheimer approximation. I have just told a term like Born-Oppenheimer approximation. This is a type of a quantum mechanical approximation that I take up while solving the Schrodinger equation for that particular system in my quantum mechanical computation. So what is this Born-Oppenheimer approximation? So you just consider a hydrogen atom, because beyond hydrogen atom you cannot go. Even at the level of Born-Oppenheimer approximation, you can do only at the level of Born-Oppenheimer approximation, you can work for hydrogen atom. Beyond that, if you cannot do with pure theory, like pen and paper theory. So this Born-Oppenheimer approximation, what does it mean by that? This particular term. It's very simple. See, you just take a hydrogen atom, you have a nucleus and you have one electron there. And in general, both nucleus, there is nothing staticness in the quantum level. So both nuclei is moving and also the electron is also in motion. Both nuclei and both that nucleus and the electron, both these entities in hydrogen atom. I'm talking about atom now. Hydrogen atom. These two are in a status of motion. So now in Hamiltonian operator, you have a term called nucleus electron attraction, isn't it? There is a term called nucleus electron attraction. So that will actually include, that attractive potential will include 1 by the straight line distance of separation between the proton and that means the nucleus and the electron. Q, charge of the nucleus into charge of the electron divided by straight line distance of separation between these two charges. That is the electrostatic attractive potential, the whole into 1 by 4 pi epsilon 0. That's the Coulombic interaction potential in line with attraction. So it includes, effectively it includes 1 by r, 1 by the distance. And you have studied, if both the entities, quantum entities are moving, you cannot have a very specific definition of that r, isn't it? Because Heisenberg will become unhappy in that context. Because there is an Heisenberg's uncertainty principle, which was put forward by Heisenberg, which basically says, if I say like using that, I find out the electrostatic attractive potential energy accurately. If I say, I might have done some mistake with respect to positioning of this. If I say the positions are correct, there will be some uncertainty based error that happens in the total energy that has been computed. So what effectively happens is, because of these levels of uncertainty aspect, you need to fix the position of any one of it, either nucleus or the electron. And owing to a huge difference in mass between the nucleus and the electron, generally what we assume is, with respect to the point of view of electrons, the nuclear coordinates are considered as fixed. That means it's something like a frozen nuclei approximation. The nucleus is considered as static. So what alone is moving now? Only the electron alone is moving. Now it has born, the two moving body problem has got subsided into or reduced into a one moving body problem, which to a considerable extent you can address. So this approximation where you consider nuclei of a particular nucleus of a particular system, particular atomic system, the nuclei in a molecule, various nuclei in molecule are fixed in their position, because I am focusing from the electronic structure point of view. So from that point of view, if I assume that it is basically fixed, the coordinates of nuclear coordinates are fixed, I am doing my computations at the level of Born-Oppenheimer approximation. So these kinds of approximation, another approximation is like independent particle approximation, then our Huckel's pi electron approximation, which most of you will be knowing at least at the basic level. So these are some of the approximations that you will generally be applying in almost all our quantum mechanical computations. Now going to the next. I've just explained about that. I'm not going to the minute details of this right now because that's not needed. That will actually solve. I mean, that actually will need a much more time right now. That's not needed now. That's not the purpose now. Now, I'll just tell you a few applications of a particular semi-empirical quantum mechanical calculation. It's a semi-empirical quantum mechanical. That means partly experimental, partly theoretical. Basically originating from the rigorous quantum theory. So from the Huckel's pi electron approximation, I will concentrate only on the pi electronic structure. For example, if I just want to solve electronic structure of pi electronic structure of ethylene, if I concentrate ourselves on only onto the pi electrons alone, it is only a 2 electron system instead of a 12 electron system. Otherwise, it has now come to a 2 electron system with the application of Huckel's pi electron approximation. And with that, if I solve Schrodinger equation, there are provisions to calculate charge densities on atoms, the concept of aromaticity and anti-aromatic behavior, aromatic behavior and anti-aromatic behavior of molecules. You can predict it by using Huckel's molecular orbital calculations. Then the electronic spectra of such compounds you can predict by using HMO calculations. Bond order calculations you can perform. Free valence index based calculations you can perform. And the sites of preferences, like where an electrophile will attack on the molecule or where a nucleophile will attack on the molecule. All these kinds of things you can basically predict by using these kinds of calculations. Okay, so I've just mentioned a few applications in line, and based on this you are learning about the molecule. That's the ultimate requirement for chemistry, isn't it? So these kinds of calculations you can perform. I'm just giving you some glimpses. Now coming to the next, Hartree and Hartree for computation. I don't go much into the details of this. You please understand that there are several methods of computations based on which all these quantum mechanical methods based on which all these computations are done. A lot of mathematics is involved in this, all these computations. So I've just told you a little about this. Then basis sets, a few basis sets and those kinds of things. Then already certain quantum mechanical packages are there, software packages are there. Now the thing is, like, there are well written algorithms written for solving Schrodinger equation for various systems in various contexts. You have various software tools for that. So some of the tools are like Gaussian, Material Studio, Spartan, Orca, Gammas, Quantum Espresso, etc. Some of them are free and some of them are paid softwares. So you can some of them Orca, Gammas, Quantum Espresso, etc. are free. Probably for academic purposes you can download it and then utilize it for learning purpose. Fine. Then molecular mechanics. The next way of approach in computation is molecular mechanics. That means you will be applying the classical mechanics based principles to study about properties of systems. So there we will be working with terms like force fields, where instead of quantum mechanical equation, so Schrodinger equation, we will have fundamental equations talking about stretching potential, bending potential, torsional potential, electrostatic potential, and non-covalent interaction based potential. That is Lennard-Jones potential. That's what is written here as a summation over E stretching, E bending, E torsion, E electrostatic, and E LJ. So these are specifically having different mathematical structures. I'm not going to the fundamental details of those detailed mathematical structures of these individual equations here. But please understand, each structure has got its own extensions, probably in terms of your Hooke's law, you know, Hooke's potential. Suppose a molecule is considered, for example, a diatomic molecule, if you consider, you assume the chemical bond as a spring and the two atoms as rigid spheres. So a vibration can be, the potential of that system can be told as equal to half kx square, like our potential energy connected with is a mass attached to the end of a spring. So this is the way in which classical equations are developed. These are basically the classical laws based on which energy computations are done. So I have just given some examples connected with various types of potentials and those kinds of things. Then there are various algorithms, just like as quantum mechanical algorithms, there are various algorithms which make use of classical mechanics formulas also to solve properties of systems. They are basically the molecular mechanics based calculations. So some of the things that I've told here. Now in connection with application, I've just told, I've not discussed anything about simulation. So now the thing is like you model a molecule and predict its properties. Now, whenever you are talking about the time evolved or temperature evolved behavior of systems, you will be in fact speaking about simulation. So modeling and simulation. Simulation means, for example, with respect to the variation in pressure, what happens with the properties of a molecule? With respect to variation in temperature, what happens with the properties of molecule? With respect to a change in time, over a period of time, what happens with the property of that molecule? Such processes, if you model, that aspect is actually called as molecular simulation in general. You have titles like MD simulation, MC simulation, CPMD simulation. These kinds of techniques are there. Probably all these techniques basically involves lots of mathematics, and details can be discussed in probably in another session. So towards the end, I'll just tell about one significance with respect to the application of this computational chemistry. And obviously it is utilized nowadays extensively in design of materials and processes. One major area where it is applied is drug discovery. Generally, it used to take about 25 years from concept to market for a particular drug molecule. For example, if there is put out of a disease, from concept to market for a drug molecule to come up, it used to take about nearly 25 years. Now, with the application of computational chemistry, that time lag has become considerably reduced just to 9 to 10 years. I'm telling some average range only. Case to case, there may be differences. And obviously, the supporting domains of computational chemistry are like bioinformatics, chemoinformatics, machine learning, that is artificial intelligence, support vector machine, pharmacogenomics. All these kinds of domains basically contribute a lot to pure computational chemistry in drug discovery process. This is one of the applications which I wanted to tell you, because in a recent time we have experienced this in connection with COVID. Within a span of nearly 1.5 to 2 years, all of us got administered with the vaccine, purely because of the advent of computational chemistry techniques and integration of computational chemistry techniques with biotechnology, bioinformatics, chemoinformatics, artificial intelligence, data mining, all these things put together. It's actually a collective work, but computational chemistry has contributed a lot in that line. The molecular modeling, simulation types of works in research has contributed to that. So I think with that, I'll wind up the discussion right now. A little more details about mathematical details and all probably in some other session, or if you are joining a course on chemistry for your higher studies, probably you will study details of this in future. So I think I'll wind up right now. So is it okay?
Yes, sir. It's very okay. Sir,
yeah, you have about 4 or 5 minutes. If any questions are there, happy to answer. I'll just come to the normal screen.
Probably there are not many questions.
Okay.
So, sir, well, thank you so much for such a beautiful session, sir. It will be useful for our participants and everyone who is watching this session. So, probably, I have to thank all the participants also. Well, see you, all of you, next Saturday. Thank you. Thank you.
Thank you. Right. Thank you.